Okay, so we're coming to the end of week 2. Just want to show you in Moodle where we are. So today we're taking a quiz on lectures 8 through 16 after we answer a few questions for 30 minutes or so. You'll notice that I added a folder here that wasn't there before Tuesday, and I did the same thing in week 1. And in this folder are the notes I wrote on the board on Tuesday. Everything that I wrote there is in this PDF, and then there's a link to the video from class on Tuesday. So if you ever kind of like didn't quite catch something that I was doing in class, you can always go back and watch the video or look at the notes. Or if you missed class, you can do that too. Okay, so the characteristics of a periodic function. So I draw an example here. Just any old periodic function with a wave. The period is the length of one full wave. Okay, so I always measure it from peak to peak. I think it's the easiest way to sort of pick out the period. How long does it take to get from high point to high point? So this distance is the period of the wave. So you can think of the tides as a periodic function. They come in and they go out, and they come in and they go out, right? The water gets higher and lower and higher and lower. So think of it like the distance, the length of time between high tides, right? That's the length of one full period, one full tidal cycle. And then the midline is the line that's halfway between the high and the low point, right? So this would be a maximum right here, and this would be a minimum. This is the midline. This line that's sort of halfway between the high point and the low point, we call that the midline. In this particular picture, it's the x-axis. It's not always the x-axis, but it's always going to have the form y equals some number. Right? In this picture, it's y equals 0. The x-axis equation is y equals 0. And the amplitude, right? So the amplitude is the distance from the midline to a high point or a low point, and it's a distance, so it's always positive, right? So it is going to be the distance from a low point to the midline. Or a high point to the midline. Always positive. Frequency, don't worry about frequency. We don't really. It's related to the period. So the period is the length of one full wave. The frequency, I think, is the number of full waves you can fit in 180 degree or 360 degrees, something like that. I can't remember. Don't worry about it. We're always going to talk about the length of a wave in terms of its period as opposed to its frequency. All right, can you go over how to find angles only using the unit circle? How to find angles of what? Who asked this? What do you mean? Oh, so not how to find angles, but how to find trig functions of angles? Sure. Okay. Okay, so here's a unit circle. If I pick any random angle on here, we'll call this angle theta. The place where that angle, right, we start measuring from the positive x-axis up to that angle theta. The place where this terminal side of my angle hits the unit circle has some coordinates, right? X and Y. So we define the trig functions as the cosine of that angle is always the x coordinate of where it hits the unit circle, and the sine of that angle is the y coordinate where it hits the unit circle. So if I wanted to find the sine of 90 degrees, say, I would draw a little unit circle. And this is something you should get used to doing. Like draw a unit circle should be like, for me, I do it all the time because I have a hard time picturing the whole thing in my head, so I have to draw it. So you just quick unit circle and you say, okay, 90 degrees, that is right here. It's this angle, right? So I figure out, okay, what are the coordinates of that point right there? 0, 1. Yep. Oops. 0, 1. So the sine of 90, sine is always the y coordinate where it hits the unit circle. So the y coordinate in this case is 1. So the quadrantal angles, 90, 180, 270, 360, those are kind of easy because it's easy to come up with the coordinates. Have you done, like, I can't remember if it's in the lectures yet, like if I sine of 30, just using the unit circle? Yeah, okay, so let's do that. Let's say we wanted to find the sine of 30 degrees. So you'd go, unit circle, draw in 30 degrees. And you need to know the coordinates of this point. And I can derive them for you, but you do need to memorize them. Or have a picture of a unit circle that you bring with you to every quiz and test and sleep with under your pillow. Okay. So the coordinates of this circle we can derive by dropping a perpendicular here. We know the hypotenuse is 1 because this is the unit circle and that's its radius. And who remembers their 30, 60, 90 degree triangle relationships from geometry in high school? My students still in high school. Great. Okay. So the hypotenuse is always twice which leg of the 30, 60, 90? The shorter one. Good. Okay. So that's one. And the shorter leg is always opposite the smaller angle in a triangle. So the 30-degree angle is opposite the shorter leg, and the shorter leg is always going to be half of the hypotenuse. So this would be a 1/2 right there. And the longer leg is always the shorter leg times square root 3. So this is square root 3 over 2. So to get to this point, you have to go square root 3 over 2 to the right, and then 1/2 up. Those are the coordinates of the point. So the sine of 30 degrees would be 1/2, the y coordinate. Alpha. Yeah, that's the Greek symbol alpha. Yep. Oh, yeah. Okay. So typically in algebra, you name unknown things letters. And in geometry, we name unknown lengths letters. Like, so if I have a triangle, and it's going to be A, B, C. So this is just conventions. You name the vertices capital letters. The length of the side opposite capital A, we tend to call little a. The side opposite capital B, we call little b, and it represents the length of that side. and then we'll call that little c. And then you can either just name the angle by this capital letter, but sometimes it gets confusing, like if there were another line coming out of there. So then we might name the angles alpha, beta, and gamma. You can just name them CAB in this case, but if this were a more complicated picture, right? So there was, if I said angle capital B, you know, which one would I mean? Sometimes we tend to use Greek letters for the angles. Does that make sense? Right. So in a unit circle, if I pick a random angle alpha, right? I just drew a random angle there, alpha. If I wanted to mark 180 minus alpha, I would say, okay, well, 180 is this whole distance here, but I have to go that whole distance and then subtract an angle that looks like alpha. So I would draw alpha over here. Yeah, so then I would do 180 and then go back by alpha. So this angle right here is 180 minus alpha. And then you might notice that when I drew it, I kind of drew this badly, but this point and this point are related geometrically in that they're reflections over the y-axis. So if you know the coordinates of this point, you can get the coordinates of this point by just making the x coordinate negative. And let's say I wanted to do 360 minus alpha, right? I would do a whole circle around, and then I would have to go backwards by the angle alpha. So I would say, okay, well, alpha is like about this big. I want to put it right here, right? So that's about the same size as alpha. So I go 360 and then go back by alpha. So my angle is actually to this green one right here, 360 minus alpha. Yeah, and then this point and this point are related in that they're reflections over the x-axis. So same coordinates, except that if this is xy, this is x negative y. Yeah, so if you know this point, you can get the exact coordinates of all of these other points that they were asking you to get. All right, so we're looking at number 7 from homework 9, making a line of best fit. So the first thing they ask us to do is just do a line of best fit, straight linear regression. So in GeoGebra, the way I do this is I highlight these coordinates and I right click and I choose create list of points. And the specific directions on how to do this are in that handout I gave you. I think it's yellow GeoGebra reference sheet. It says how to do this. Or you can use your graphing calculator if you know how to do that. All right, so I've got my points. I don't need to see this spreadsheet anymore. I can't see them. I just have to adjust my window to be able to see them. So let's see, my x's go from 8 to 37. So I'll go with 40. And then my y's, the smallest one's 21, and the biggest one is like 7,000. Okay, there, now I can see them all. All right, so the way I fit a line to my data points is I use the command fit line. And then it just asks, as I type fit line, up pops the command fit line, and it tells you what you have to input to that command. And you just have to give the name of the list of points. And my list is named list 1, is the default name. So fit line, oops, square bracket, list 1. And we have a line. And the equation of the line is up here in the upper left. Just drag that So you get 228x minus 3,434. And then if you want the correlation coefficient, in your calculator, it automatically comes up. In here, you have to give another command, correlation coefficient, and then the list of points, which is list 1. And we get a correlation coefficient. They named it B, but it's just the correlation coefficient, and it's 0.81. No. Okay, so that's one way to fit a line, is to take the first point and the last point and connect them, but it's not the best way. The best way is, the best way is a much more complicated algebraic thing, which is why we have the computer or the calculator get it for us. Yeah, so this is the line of best fit, which means that it's the line that minimizes all of the distances from the points to the line. Yeah. You're welcome. Okay, we'll go over this one and then I'll give you your quiz. Okay, so the Richter scale measures the strength of an earthquake, and the strength of the seismic waves of an earthquake are compared to the strength W sub 0, which is the seismic waves of a standard earthquake. And so W sub 0, they're not telling you what that value is. It's the strength of the smallest recordable earthquake, like the smallest earthquake that the machine is sensitive enough to notice. And then the Richter scale is determined by taking the log of the strength of the seismic waves of the earthquake divided by the strength of the seismic waves of the standard earthquake, the smallest possible seismic waves. All right, so the question is, in 2008, the Sichuan earthquake in China had a Richter scale rating of 7.9. How many times more powerful were the seismic waves of that earthquake than the standard seismic waves? Okay, so I need to find the value of W and compare it to the seismic waves that are standard W0, right? The seismic waves of the Sichuan earthquake, those are W. So I need to compare them. How many times more powerful? So when I want to know how many times bigger one thing is than another, how do you do that calculation? Like if I make $50,000 and somebody else makes $10,000, how many times bigger is my salary? 5 times. How'd you get that number? You divided. Yeah, you do the bigger one divided by the smaller one. So I'm looking for W divided by W0. Does that make sense? Okay. So I know that my Richter scale rating is 7.9. So I'm looking for W divided by W0, so I can just solve for this. It's already written into the equation. So there's a little hidden base 10 here. And then what's the trick? How do I figure out what W over W0 equals? Switcheroo, yep. Yeah, it's switch from log form to exponential form. 10 is your base, 7.9 is your exponent, and that equals W over W0. And then you just type that into your calculator, 10 to the 7.9. So 10 to the 7.9 is almost 8 million times as strong as the smallest possible recordable earthquake. All right, what if I took this question a step further and said, okay, there was another earthquake somewhere else in the world that had a Richter scale rating of 6. How much stronger are the seismic waves of a 7.9 compared to the seismic waves of a 6? So 7.9 compared to 6. How much stronger? So I'm going to write two equations now. 7.9 is equal to the log of W over W0, and 6 equals the log of W over W0. And in both of these, I need to figure out what W is. I need to know the strength of the seismic waves of each of these two earthquakes. And then to figure out how many times bigger one is than the other, you divide. Right? So I could call this one, say, W1, and I'll call this one W2, because they're really two different variables. All right, so to solve this equation for W1, I would say 10 to the 7.9 is equal to W1 over W0, and then just multiply both sides by W0. So I have W0 times 10 to the 7.9. That's the strength of the seismic waves of earthquake 1 for a 7.9 Richter scale. Earthquake 2, solve this one for W2. So I have 10 to the 6th power is W2 over W0, and then just multiply W0 to both sides. So the seismic waves of earthquake 2 is W0 times 10 to the 6th. So if I want to know how much bigger W1 is than W2, is how much stronger the seismic waves are, I just divide W1 over W2. The bigger divided by the smaller. So I have W0 times 10 to the 7.9 compared to W0 times 10 to the 6th. Turns out I never needed to know what W0 was because they cancel. And then how do you do 10 to the 7.9 divided by 10 to the 6th? Subtract. So this would be 10 to the 1.9. So that's how many times as strong it would be. Uh, 79 times as strong. Does that make sense? Okay, good. Don't forget it.